Hello everyone, how are you doing? Welcome to another exciting session. So today we're going to be looking at time series analysis, where we're going to try and predict the central bank of Kenya rate. That will be on a meeting that will be held on next month, and you're going to try and use a time series model to predict that. If you have any questions, just leave them in the comment sections, and don't forget to like, share, and subscribe for more content like this. Let's dive right in. So we'll be using Python today, and as usual, if you've watched my previous Python videos, my best form of starting my work is by importing the necessary libraries, and as you can see, that's what I've done. If you're coding, don't forget to pause the video at any point to be able to copy the codes, okay? So those are the necessary libraries that will be needed for the for the whole process of today. And the next thing is to load your datasets. So I have the inflation rates dataset and the central bank rates dataset. So this dataset, you can access them from the Central Bank of Kenya dataset, where they have various datasets. So you can go to their website and you can get the inflation rates as well as the central bank rates. So after you've loaded your dataset, it's always good to check whether you've loaded the correct dataset, and we do this by just looking at the first 5 entries. If you want any number of entries, you can basically change over here, but the default one is, if you want the first 10, you can just change there. If you want the first 7, you can change there. But for my case, I just view the first 5 and we move on. So you can see we have three variables. We have year, month, and 12-month inflation for the inflation dataset. And then for the central bank rates dataset, we have the year, month, and central bank rate. And as you can see, our data is very fine because the year is 2025, the month is June, May, April, March, and so forth. Then we have the 12-month inflation in form of decimals, of float, and so forth and so forth. So we are going to model, you're going to try and predict the central bank rate, but you're going to use the inflation as an exogenous variable. And to do this, we need to merge these two data sets, and we need something unique, or maybe I can say a unique thing to merge them, okay? And a unique thing we can use is if you combine the month and the year, because you cannot have June 2025 twice, you cannot have March 2025 twice in a year. So we're going to do that, and to do that, in each and every data set, we add a date column where we're going to have it as the year will be the year column for the inflation data set, the year column, then the month is the month column, then you're going to leave the date as, we'll fill it with a 01, and then so we're going to have the year is 25, the day is 01, the month is June, and so forth. Then we'll have the rates data set. We'll also create a date column where we'll have the year, the day, and the month. So whereby the day is 01, the month is as in the month column, the year as in the year column, okay? And then you're going to set it as an index. Right. So now, since we're only working with we're only interested in the inflation rate and the central bank rate, so we're just going to select the inflation rate and the central bank rate from the inflation dataset and rates dataset respectively, and then we're going to merge them using the index. You remember we have set the date column in each of those datasets as our index, so that's what you're going to merge them, okay? And as you look at our new data frame, which is labeled as df, you look at the first 5 entries. We can see we have the date, we have the central bank rate, and then we have the 12-month inflation. And if you want, you can now confirm these using in your datasets, like using your original datasets. I did that, and yeah, they did match all of them. Not, I did not look at all of them, you just look at them at random. You can say maybe pick the 7th, maybe the 10th, and so forth. You cannot look at all of them, 228 with your eyes. It's kind of not realistic. Okay, So let's now have some info about our data set. Let's describe our data set. Let's see our data, if at all our data set has some none or empty values. And so for we have the column, we have the central bank rate, and we have the 12-month inflation. We have 229 entries in both of them. There is no empty entries. Then each of the variables are float data types, which is good. And then now we have our central bank rate and 12-month inflation descriptive statistics, where we have 229 entries in both. The mean central bank rate was 9.35. The average difference between the entries and the mean was 2.43. The minimum central bank rate was 5.75. The maximum central bank rate was 18. The first quartile, the second quartile, and the third quartile were 8, 9, and 10, respectively. So let's go to the 12-month inflation. So I'm reading from here. So the average 12-month inflation is 7.198. The average difference, or the standard deviation, which is the average difference between the values and the mean, is 3.86. The minimum value is 1.85. The maximum value is 19.72. The first quartile, the second quartile, and the third quartile are 4.84, 6.26, and 7.88, respectively. And as for our category, or not our category, but our variables, the central bank rate and the 12-month inflation rate both do not have NAs. And therefore, in terms of missing values, our data is clean. Okay? So now we go and have an overview, or a plot, or a time plot for each of these variables, that is both the inflation rate and the central bank rate, to see if we can observe any pattern in any of them. And again, just pause the code, just put the video so that you can copy the code if at all you're coding. So let's go to the time plots. And as you can see, for the central bank rate over time graph, you can see it actually started at around 9.75 or about. Then it went to 10, maintained at 10 for, between the years 2006 and 2007 thereabout. Then went down, then up, then came down, came up, been decreasing over a while. Then it went up again, and it's been decreasing over a while right now. And you can see there's a kind of a cycle where it comes, decreases, then increases, then decreases again, remains constant, increases again, remains constant, and decreasing at an interval, then rising again, and then decreasing. Okay, so you can see that pattern. And for the 12-month inflation over time, again, it's been ups and downs. So it's been from low to up, then from low to low again, to up, then to low. It's kind of within a margin of the years 2013, mid 2013 to around 2017. It's been up and down over certain values, which is around 5.4 thereabout, and 7.9 or 8 thereabout. Then up, then constant. Then okay, you can see for the 12-month inflation over time, it's not that much of a noticeable pattern. It's kind of going up, then down, then remaining constant in a way over time, and so forth and so forth. And over the past, say, this from 2023 or mid 2022, it's been decreasing all along. Just a slight increase over here, and for the central bank rate, since same time, not same time, but around March 2024 or March or April thereabout, it's been decreasing and decreasing all along. Okay, so we can see for the central bank rate over time, there is a cyclical pattern, but for the 12-month inflation, no noticeable pattern at all. Okay, so now when you're doing a time series model, one of the assumptions is that your time series data is stationary. Okay, and it's good to check for stationarity. So we are going to use the augmented Dickey-Fuller test to test for stationarity, and the level of significance is 0.05. And we have the null hypothesis is that the data is non-stationary, and the alternative hypothesis is that the data is stationary. And so we can see our p-value for the actual time series data, or the central bank rate. It's 0.03. That's the p-value, which is less than 0.05, and therefore we reject the null hypothesis and conclude that as 95% confidence interval, our series is stationary. Now, when you look at the p-value for the differenced time series data, so I have differenced the time series data, and if you look at the p-value is 2.49 exponential negative 0.7, not 0.7, exponential 7, and that's a value close to 0, and therefore still the difference data exhibits stationarity. Why did I do this? So I wanted to do this so that if at all my time series data, the rate was not stationary, then the difference time series model, if you find your data is not stationary, it's always recommended for you to difference it, not at least one month. Once you difference it once or twice, going beyond twice, it's overdoing it. So we can see that the original time series data is indeed stationary, and also the difference data is also indeed stationary. So let's go to the plots, and we're going to do the SCF plot and the PSCF plot, and we can see that our SCF values, they lie within 0, and as you can see they range from negative 0.25 all the way to 1. This is just one of them that is going to 1, but in general most of them lie between negative 1 and not negative 1, negative 0.15 thereabout, and 0.15 thereabout, okay, which is good. And as you can see, kind of exhibit a pattern, okay. So we expect them for a good time series data, you expect them to be just a rectangular pattern, but as you can see, there's a pattern, there's a kind of cyclic pattern over there. Then when we look at our PRCF, again, all of them lie within 0, and most of them lie between negative 0.1 and 0.1 thereabout. And again, over here you cannot see, it's also kind of a pattern, you can see, which is not a good sign. So again, for both the SCF and the PSCF, we expect them to be in a rectangular way, not exhibiting patterns such as a funnel, or you get me. Okay, so it's now time to prepare our data for modeling, and we're going to split our data from June 2006 to December 2024, all the way to then from January 2025 to June 2025, whereby we're going to have our training set running from June 2006 to December 2024, and our test set from January 2025 onwards. And now we're going to be using the SARIMAX model, and as I've told you, this is because we are using another variable that is proposed, or I can say I thought or I think might be affecting the central bank rate, which is and that variable is the inflation rate. Okay, that's why I'm using the SARIMAX model. So our endogenous variable is the central bank rate, our exogenous variable is the 12-month inflation, our non-seasonal components values, which is PDQ, are 1, 1, and 1, and then our seasonal component values, which is PDQ and Ls, are 1, 1, and 12 respectively. We are going to see our residuals, and then we are going to see the residual summary. Okay, so when it comes to time series modeling, again, if you've done machine learning, machine learning, you basically have to evaluate your model. And if you're combining different models, say maybe a random forest, a decision tree, a logistic regression, and you want to compare both of them, there are some metrics you use so that you can compare them. You use something like you use some metrics like R squared and RMSE to compare them. So when it comes to time series model, again, there are metrics that you're supposed to use to be able to distinguish which model is best fits your data. Okay, so we have various of time series model. We have the AR, we have the AMA, we have the ARIMA, we have the SARIMA, we have now the current one is the SARIMAX, we have the ARCH, we have the GASH, and so forth. So when you're comparing these models, what are the metrics that you use to distinguish which model is the best to use? So number one, we have the log likelihood, we have the AIC, the BIC, and the HQIC. You also have the sigma squared. Okay, then you also have the skewness and the kurtosis, okay, to compare the models. So for a log likelihood, so from our current model, we have negative 203. Okay, so any models that have a higher log likelihood will be a good fit, but any model that have a lower log likelihood will be a bad fit from our model. Okay, and then for the AIC, for the BIC, and the HQIC, they all hold the same principle. So a model, so let me go with the AIC, which is 118.562. So any model that will exhibit a lower AIC, BIC, and HQIC than our current values, then that's a better model. Any model that will exhibit a higher AIC, BIC, and HQIC value from other than this any higher value of AIC, BIC, or HQIC, that's a poor model. So when it comes to sigma squared, we look at the coefficient value over here. So there is 0.343. So any model that exhibits a higher value of sigma squared, then that model is a bad fit. But any value that exhibits a lower sigma squared, then that's a good fit. Okay, so looking at skewness and kurtosis. So any value close to any model that exhibits a skewness close to 0, that's a good model. Okay, then kurtosis is still the same. Any model that exhibits a skewness close to 0 is a good model. Hope you now know how to interpret your and compare your models. Okay, so now let's look at the coefficients of our model. So we have the 12-month inflation, we have the AR1 component, we have the MA component, and then we have the AR seasonal component, MA seasonal component. And so let us look at them if they are significant to our model. So we will do that by comparing the p-values, and we have the 12-month inflation. We have the p-value is 0.456, which is greater than 0.05, and this tells us that the 12-month inflation is not significant. So again, you see, this is data. There's something, there's your own intuition, and then there's now testing the data. So according to me, I saw that the 12-month inflation is kind of affecting the central bank rate. But what does my model summary tell me? It tells me that the 12-month inflation is actually not significant in telling me whether, or in trying to predict the next central bank rate decision. And then when I look at my AR1 component, my MA component, the non-seasonal part, then they are both 0.00 and 0.029 respectively, which are both less than 0.05, and this implies that they are significant in my model. And then when I look at the AR2 and the MA2, 0.363, 0.52. Sorry, it's the the AR1 component, the AR1 the seasonal part, and the MA1 the seasonal part. They are 0.363 and 0.525 respectively, which are both greater than 0.05. And what this tells me is that the AR1 and the MA1 in the seasonal part are not significant. So what I can do to them is just set them as 0 and 0, or yeah. Okay, so let's look. So when you're coming up with the time series models, again, one of the assumptions that we looked above is that the model is stationary. So another assumption is that your variances are equal and the residuals are normal, and there is no autocorrelation. Okay, so that's what we must check in our model. Okay, so to check for autocorrelation, we are going to use the Junebox test or test statistic, or yeah, the Junebox test statistics, where we're going to now look. We are not going to compare with the test statistic, but you're going to look at the p-value. So we have the null hypothesis for the Junebox test is that the null hypothesis that there is no autocorrelation, whereas the alternative is that there is autocorrelation. The p-value is 0.80, and this implies that there is no autocorrelation because we fail to reject the null hypothesis. Now, looking at the heteroscedasticity p-value, the heteroscedasticity is simply an equal variance, whereas homoscedasticity is equal variance. So, the null hypothesis is that there is homoscedasticity, or the variances are equal, and then the alternative is that there is heteroscedasticity, or unequal variance. So, when you look at a p-value is 0, which is less than 0.05, and this implies that there is presence of heteroscedasticity. So heteroscedasticity is a problem in our model. So when we exhibit this kind of problem, we go to other models such as the GASH model, the ASH model, where they are just for example, the GASH is the generalized autoregressive model conditional heteroscedasticity. Okay, so you try other models and see if they're still going, they will be a good fit for your data. But I also tried the GASH and the ASH, also the SARIMAX and the combination of the SARIMAX and the GASH, but still none of them performed better when it comes to the comparing the values, the HQAC, the BIC, and the AIC. When it comes to comparing the log likelihood, when it comes to comparing the skewness, kurtosis, and also when it comes to comparing prediction and also the significance of, the parameters, some performed worse than the current model. So then the Jacobera is used to test for normality of residuals, and where we have the null hypothesis that the residuals are normal, and the alternative is that the residuals are not normal. As we look at our p-value over here is 0, which is less than 0.05, and that implies that our residuals are not normal, which is, so in our model we have two problems: the unequal variance and non-normality of residuals. And so for non-normality of residuals, one thing you can do is this is the Box-Cox transformation. You can do some transformation to your data to make your residuals normal. Again, I tried this. I tried the Box-Cox transformation. I tried the square root transformation. I tried the logarithm transformation. Still comparing the parameters, none of them performed best. So if you have a way in which you can get a better model in terms of when you compare in terms of metrics, just don't forget to share your comment below. And so now let's compare and evaluate our model and see how it performed, comparing the training set and the test set and the predicted values. Okay, so the MSE is 0.1663. Okay, the mean squared error. And then so what we use is the RMSE. So the square root of the MSE, this is approximately 0.167 or 0.17. So the square root is around 0.4 something. Okay, so this tells me that the difference between the actual value and the predicted value is 0.4. Now, what does that mean? So if we look at our descriptive statistic here, the minimum value was 5.75. The maximum value was 18. Okay, so having an RMSE of 0.45 or 4 something thereabout is really not good, bearing in mind that the central bank rate decision is either an increase or decrease by 0, 0.25, 0.5, 0.75, or even 1. That is most of the times. They vary between 0 and 1, and the values must be a device divisible by 0.25. So you can see having an RMSE of 0.4 something is really, really bad, because our values change between 0 and 1. It's either an increase or decrease by 0, 0.25, 0.5, 0.75, or 1. So that tells us that our model was not a good fit. And so now let's go into our plot over here. So our trained data, as discussed earlier on, it was running from June 2006 to December 2024, and then our test data was running from January 2025 to June 2025. And then so our predicted or our forecast, you can see it's kind of off. The orange line represents our test data, the green line represents our forecast data. If at all I'm wrong with the colors, please forgive me, I'm a boy child. So you can see it did not do a good prediction. As you can see, yes, it is decreasing, but it's not kind of good. Okay, but comparing to this model to all my other models that I tried out, this one stood out in terms of predicting, in terms of the metrics as well, and so I had to go with this one. Okay, now we're going to do what we call a step ahead forecast. So our data is in form of months. So we have June, July, August, January, February, March, April, and so forth. So our data is in form of months. So what I'm trying to do, or with the goal and the objective for the modeling, is to try and predict the month of August. Okay. Now remember, our training data was all the way to December 2024. So we are going to now do an 8-step ahead forecast to be able to reach to the month of August. Okay. So what I mean by 8-step ahead forecast, it means that it will predict the values for 2025 January, 2025 February, all the way to 2025 August. That's what I mean by an 8-step ahead forecast. So if our data set was in terms of years, and my data set ran up to 2024. So for an 8-step ahead forecast, it will predict data, yearly values, all the way to the year 2032. So I hope you understand. If it was in form of days and I was in what day, maybe say I was in Saturday or Sunday, and say I do a 4-step ahead forecast, it will do for Monday, Tuesday, Wednesday, and Thursday. So that's what I mean. And so I did an 8-step ahead forecast. So if you're copying the code, just pause the video and you can copy that. So now this was the 8-step ahead forecast. So for the month of January, it predicted the rate to be 10.82, February 10.63, March 10.46, all the way to August, which was 10.221. But again, remember, this rate is made. It depends on when it's made. It can be made every month. It can be made 2 months, but it should be made after each and every 2 months. That's the way it goes. It should at least once every 2 months. Okay. So the trend has been the decision was made on December 2024, then made on February, then made on April, then made on June, and then now it's going to be made on August. So if I look at the previous decision made, that was June, which is this value over here. It was at 10.23. That's not the actual. The actual, let me show you the actual. As of June, it was 9.75. Okay. So the predicted one was 10.29, which is approximately 10.3. Whereas the predicted for August is 10.22. So that's 10.29 minus 10.22. That should be 0. That's 10.3 minus 10.22. That's around 0.78. Yeah. So 0.78 difference. Is it? 10.3 and 10.22. 10.22. That's a 0.08. Yeah, not 0.78. 0.08 difference. So 10.3, 10.22 is 0.08. And this is a very low rate, which approximately 0.08 with the rounding off to one decimal place around 0.1. And so, as you can see, our predictive values say that the the month for the month of August, the rate is going to decrease, but by a slight amount. Okay, now the slightest of 0, 0.25, 0.5 and 0.75 and 1 is 0, but 0 means no change. Okay, so for a decrease I'll go for 0.25, and therefore according to our model our interest rate is approximately going to go down by a rate of 0.25, and that means the most likely decision that will be made on August is that the central bank rate will stand at 9.5. And thank you for going through the end of this video. I really appreciate that. And if you found this content to be valuable and interesting, make sure to like, comment, share, and subscribe for more content like this. And I'll see you in the next one. Have a good time. Bye bye.